Bismillahirrahmanirrahim. Assalamu alaikum, dear student. The topic of our discussion is ionic bond in bonding in solids. So far, we have discussed the bonding in solids. Moreover, we have discussed the details of some ionic bonds. In ionic bond, we have discussed many things. For example, ions and ionic radii of different uh, compounds like lithium fluoride and sodium fluoride, etc. And we have discussed some variation of electron density along the line connecting to these compound like lithium and lithium fluoride, and as a function of coordination number for cations m plus 1 to m plus 4. And moreover, we have discussed the ionic structures and general principles of ionic structures. So far we have discussed all the general principles in detail, and we were discussing the point E of that principles of ionic structures. About point E, the second of a set of rules formulated by Pauling for ionic crystals. Basically, the rule means that the charge on a particular ion, for example, an anion, must be balanced by an equal and oppositely charged ions. However, since these cations, the ions are also shared with their other anions, it is necessary to estimate the amount of positive charge that is effectively associated with each cation anion bond. For example, for a cation M positive surrounded by N anions, the electrostatic bond strength EBS, electrostatic bond strength, is equal to of each bond is defined as EBS is equal to M over N. For each anion, the sum of EBS of surrounding cation must balance the charge on the anion, that is summation M over N is equal to X. For example, spinel magnesium aluminum oxide MgAl2O4 contains octahedral aluminum 3 plus and tetragonal Mg2 plus ions. Each oxygen is surrounded tetrahedrally by 3 aluminum 3 plus ions and 1 magnesium 2 plus ion. We can check that this must be so as follows. For magnesium Mg2 plus, EBS is actually the electrostatic bond strength, and electrostatic bond strength for magnesium is equal to 2 over 4, and it is 1 by 2. For aluminium 3 plus, electrostatic bond strength for aluminium is equal to 3 over 6, and it will definitely 1 over 2. Therefore, summation EBS electrostatic bond strength of 3 aluminium Al3 plus and 1 Mg 2 plus is equal to 2. We can show that their 3SiO4 tetrahedra cannot share a common corner in silicate structures. For Si4 plus is equal to electrostatic bond structure is equal to 4 over 4 is equal to 1. This is actually, therefore, for one oxygen that bridges between two SiO4 tetrahedra, summation of electrostatic bond sharing is equal to 2, which is of course acceptable. However, 3 tetrahedra sharing a common oxygen atom would be is equal to 3 for that oxygen, which is completely unacceptable. This rule of Pauling provides an important guide to the polyhedral linkages that are and are not possible in crystal structures. For example, in this table 1, list some of common cations with their formal charge, coordination number, and electrostatic EBS. While the other table, we have table 2 list some allowed and unallowed combinations of polyhedra about a common oxide ion. Many other combinations are possible and reader may like to deduce some. Bearing in mind there are also topological restrictions on the number of possible polyhedra combinations. Thus, the maximum number of octahedra that can share a common corner is 6. So Pauling's third rule concerns the topology of polyhedra and we will consider it laterally. Pauling's first rule states that a coordinated polyhedra of anions is formed about each cation. The cation anion distance is determined by the radius sum and coordination number of the cation by radius ratio. The idea that cation anion distances are determined by a radius sum is implicit to every tabulation of ionic radii. Since a major objective of such tabulations is to be able to predict correctly interatomic distances. Let us consider some of the coordination number and radius ratio rules. So now let's talk about the radius ratio rules. In ideally ionic structures, the coordination numbers of ions are determined by electrostatic considerations. Cations surrounded themselves with as many anions as possible and vice versa. This maximizes the attraction between the neighboring ions of oppositely charged and hence maximize the lattice energy of the crystal. We will definitely discuss the lattice energy of the crystal in next lecture, or if we have enough time, we will discuss the lattice energy in this lecture. This requirement led to the formulation of the radius ratio rule for ionic structures, in which the structure adopted for a particular compound depends on the relative size of the ions. This rule is useful qualitatively, but as we shall see, cannot usually be applied rigorously to explain or predict. Therefore, there are two guidelines to be followed in using radius ratio rule. Number one is the cation must be in contact with its anionic neighbors. Number two is neighboring anions may or may not be in contact. So guideline 1 places a lower limit to the lower limit on the size of the cation, which may occupy a particular site, since a situation in which a cation may rattle inside its anion polyhedron is assumed to be unstable. Using these guidelines, one may calculate the range of cation sizes that can occupy the various interstitial sites in an anion array. If we have worked systematically, if we will work systematically through problems, then the following section should be a revision. Let us calculate the minimum radius ratio for an octahedral cation site, in which the both anion and anion cation contacts occur. The cation is in contact with all 6 anion neighbors that actually applying the Pythagoras theorem, If we applied the Pythagoras theorem, then 2rx square is equal to 2rx square is equal to 2rm plus rx square. That is actually 2rx under root 2 and 2 into rm and rx, and rm and rx is equal to under root 2 minus 1 is equal to 4 414. So for radius 414, the cation is too small for an octahedral site and instead should occupy a site of smaller coordination number. To calculate the minimum radius ratio for 8 coordination, for example cesium chloride, then we need to graph Pythagorean theorem again. The 2 is equal to rm plus rx is equal to cube body diagonal. In addition, anions are in contact along with the cell edges. A is equal to 2rx, therefore 2 is equal to 2 and rm plus rx is equal to 2rx under root 3, and rm or rx is equal to under root 3 minus 1, which would be equal to 0.732. To calculate the minimum radius ratio for tetrahedral coordination, we may regard it as a tetrahedron as a cube with alternate corners missing. Anions and cations that are in contact along the cubic body diagonals, the starting equation like this one, but the anions are in contact along the cubic face diagonals, like 2rx is equal to face diagonal. So the combining that equations 3.6 and 3.9, we will get the 2rx square plus 2rx2 and is equal to 2rm plus rx square. That is the 2rm plus rx is equal to under root 6xs, and the whole value would be equal to 0.225. The minimum radius ratio for various coordination numbers are listed in this table. Note that the coordination number 5 is absent from the table in CP structure. It is not possible to have a coordination number 5 in which all metal mx bonds are of same length. The radius ratio rules are successful in predicting trends in coordination number and structure type, but can be used only as a qualitative guide. Radius ratios depend very much on which table of Ionic radii is consulted, and there appears to be no clear advantage in using either one of the more traditional sets and the modern set of values based on single crystal X-ray diffraction results. So for example, if we talk about rubidium iodide, the radius are positive, radius ratio is equal to 0.69, or we can write sometime 0.8 according to the tables based on this radius ratio. Thus one would predict 6 coordination, for example as rock salt are observed, but the other predict 8 coordination number like cesium chloride. On other hand, lithium iodide have radius ratio is equal to 0.28. According to some tables, other values predict tetrahedral coordination and other octahedrals. A more convincing example of relevance radius ratio is provided by oxides and fluorides of journal formula mx2. Possible structure type with their cations coordination numbers are silica 4, rutile 6, fluorite 8. So this would be all about this, about the radius ratio, and we will calculate, we are able to calculate the radius ratios of different compounds. Now we will talk about the borderline radius ratios and distorted structures. The structural transition from coordination number 4 to 6, which comes with increasing cation size, is often clear cut. Thus, GeO2 has a borderline radius ratio and also exhibits polymorphism. Both polymorphs have high symmetrical structures with coordination 4 and 6 respectively. Polymorphs with coordination number 5 do not occur with this compound. In other borderline cases, however, distorted polyhedra and coordination number 5 are observed. Thus, vanadium V5 positive radius ratio is equal to 0.39, while coordination number 4 0.54, and for coordination number 6 has an environment in one polymorph of V2O5, which is a gross distortion of octahedral. 5 vanadium oxygen bonds are of reasonable length in the range of 1.5 to 2 angstrom, but the 6 is much longer, which is 2.8 angstrom, and in coordination is better regarded as distorted square pyramidal geometry. It appears as vanadium V positive plus is rather small to occupy an octahedral site comfortably, and instead a structure occurs with the transitional between tetrahedral and octahedral geometry. Similar distortions occurs between coordination number 6 and 8. Thus, zirconium oxide has a borderline radius ratio point, which is 0.68 for coordination number 6, 0.78 for coordination number 8, and although it may have fluoride structure at very high temperatures, the high temperature may be regarded as more than 2000 degrees Celsius for this zirconium oxide molecule. Less severe distortion occurs when a cation is only slightly too small for its anion environment. The regular anion coordination is maintained, but the cation may rattle or undergo small displacement within the polyhedron. Like in lead titanate PbTiO3, the radius ratio for titanium is 0.59 for coordination number 6. Ti is displayed by 0.2 angstrom off of the center of its octahedral side towards the corner oxygen. The direction of displacement is reversible in an applied electric field, giving rise to a property of ferroelectricity. It is amazing that large sections of the electronics and electroceramic industries depend upon slight structural distortions occurs with borderline radius ratio. Examples includes piezoelectric sensors, high permittivity dielectric capacitors, and ferroelectric based memory switching device. So the concepts of maximum octet distance was actually proposed by two scientists named Dentis and Orgel. If the it is actually the if the metal A9 distance increases above this distance, then the cation is free to rattle. If metal A9 distance decreases, the metal ion is subjected to a compression. However, the maximum contact distance does not correspond to the sum of ionic radii, as these are usually defined, and this is also a difficult concept to quantify. Now let us talk about the lattice energy of ionic crystals. Ionic crystals may be regarded as a regular three-dimensional arrays of point charges. The force that hold them together are entirely electrostatic in nature and may be calculated by summing all the electrostatic repulsions as well as attractions found in the crystal lattice. The lattice energy, which is represented with U, is actually the net potential energy of the arrangement of charges that forms the structure. It is equivalent to the energy required to sublime the crystal and convert into the collection of gaseous ion. When we know that the sublimation is actually the conversion of a solid compound directly into its vapor state without passing through its liquid state. So it is equivalent to the energy required to sublime the crystal and convert it into a collection of gaseous ions. For example, sodium chloride NaCl found in the solid form, and we need to change the sodium chloride of solid into sodium ion positive but in gaseous state, along with the chloride ion negative in gaseous state. So the heat will change is equal to the lattice energy, which is actually the net potential energy of the arrangement of charges that form the structure. The forces that held together are entirely electrostatic and may be calculated by summing by adding by all the kind of electrostatic repulsions as well as the attraction in the crystals. The value of U, which is the lattice energy, depend on the crystal structure, the charge on the ions and the internuclear separation between the anions and cations. The two principal kind of forces determine the ionic crystal structures. Number one is actually the electrostatic force of attraction and repulsion. Two ions M positive, Mz positive and Mz negative separated by a distance R experience an attractive force F given by Coulomb's law, and this is actually the Coulomb's law. F is equal to Z positive Z negative E square over R square. Their Coulombic potential energy V is given by this equation. So short range the second thing is short range repulsive forces, which are important when atoms and ions are so close that their electron clouds begin to overlap. Born suggested that this is the repulsive force, and it is a kind of energy that it is actually the formula of this one, where V is equal to Brn, where B is actually is a constant and N is the range 5 to 12. Because N is large, V falls rapidly to zero with increasing radius. The lattice energy is calculated by combining the net electrostatic attraction and Born repulsion energies and the finding of the internuclear separation, which gives the maximum lattice energy values. The procedure is as following. For example, consider the structure of sodium chloride. Between each pair of ions there is an electrostatic interaction given in this equation. This is actually the electrostatic force of attraction. Let us first consider one particular ion, for example sodium ion, in the body center of the unit cell, and calculate the interaction between it and its neighbor, the effect of its neighbor. Its nearest neighbors are 6 chloride ions and in phase center positions at distance r. The attractive potential energy is here is given. V is equal to minus 6 E square Z plus Z negative over R. The next nearest neighbors are 12 sodium atoms, ions that at edge center position. Distance R2 is a repulsive potential energy term, and this is shown here. The third nearest neighbor are 8 chloride ions at the cube corners, and the equation is here for this 8 neighbor chloride ions. The net attractive energy between our one of the sodium ion and all other ion in the crystal is given by an infinite series like this one. This summation is repeated for each ion in the crystal. For example, for 2 ions per mole of sodium chloride. Since each ion pair interaction is thereby counted twice, it is necessary to divide the final value by 2, giving this final value. So whereas the Madelung constant A is the numerical value of the summation of parentheses in this equation 3.17. The Madelung constant depends only on the geometric arrangement of point charges. It has same values for all the compounds with the rock salt structure. Value A of some other structures will be shown later. For example, if we talk about this equation 3.18, the only factor in the lattice energy, the structure would collapse in on itself, since the equation 3.18 and this figure 3.5. This cataspore is avoided by mutual repulsion between ions or whatever charge, or when they become too close, and which is given by this equation. Here we can see this is the equation. The total energy of the crystal U is given by the summing of. Now let's talk about the Kapuscinski equations. Kapuscinski noted an empirical increase in the value of Madelung constant, which was A, as the coordination number of ions increased. For example, in the series of zinc sulfide, sodium chloride, cesium chloride, and this is shown in this table. Since for a particular anion and cation Re has increases with coordination, Kapuscinski proposed a general equation for U, which is the lattice energy, in which the variations in Madelung constant and Re are auto-compensated. He suggested that using the rock salt value for A, which is the Madelung constant, and octahedral radii, Ionic radii, in calculating Re. The substituting actually the values of R is equal to Rc and Ra and rho and Madelung constant and values of N and E into the previous equation gives actually this Kapuscinski equation. This is the final form of Kapuscinski equations, where V is actually the number of ions per formula unit, and 2 in NaCl and 3 in lead fluoride, etc. This equation may be used to calculate the lattice energy of any known or hypothetical ionic compound, and in spite of these assumptions involved, the answers obtained are surprisingly accurate. So this Kapuscinski equations is quite helpful to calculate the lattice energies of unknown and sometime known and some hypothetical ionic compound, and this equation may be used to calculate the lattice energy values of any known or sometime hypothetical unknown ionic compounds, and the results are quite satisfactory. The Kapuscinski equations was used to predict the stable existence of several previously unknown compounds. In cases where lattice energy was known from Born-Haber cycle calculations, and we will discuss the Born-Haber cycle calculations in next lecture. It was used to derive values for ionic radii. So I'm talking about the Capstan equation, where the it will be used where the lattice energy was known from Born-Haber cycle calculation. It was used to derive values for ionic radii. This has been particularly useful for complex anions. The complex anions may be the sulfate SO4 2 minus and phosphate PO4 3 minus, whose effective size in crystal is difficult to measure by other methods. So the radii determined in this way are known as thermochemical radii, and the value of thermochemical radii in angstrom of some of the complex anions are given in this table. We can note and we can study the thermochemical radii of these complex anions. It should be noted that radii for non-spherical ions such as cyanide represent gross simplification and are rarely applicable only to other lattice energy calculations. This was all about this lecture, and we will discuss some of the other aspects of ionic radii and ionic compounds and in other lecture, and we will definitely discuss the Born-Haber cycle to calculate the lattice energy of the some ionic compounds. Thank you very much.